It is section 2.3, Characterizations of Invertible Matrices. In the last section, we studied invertible matrices. An invertible matrix is defined in this way. If there is a matrix B such that both AB and BA become the identity matrix, then the matrix A is an invertible matrix. This definition of invertible matrix may not be easy to verify for some cases. So here we'll consider a theorem which is an equivalent theorem so that we consider many equivalent statements. And one of these statements is satisfied, then the matrix must be invertible. So equivalent theorems are expansions of definitions. Let's see the equivalent statement for invertible matrices. Okay, these all things are equivalent. Okay, A is an invertible matrix. Now A is row equivalent to the n by n identity matrix. That means that by applying elementary row operations, you can reach at the identity matrix. A has n pivot positions. That is the same as the columns of A are linearly independent. And here, the homogeneous system has only the trivial solution. And if we consider the matrix A multiplication as a transformation, then this linear transformation is 1-to-1 and also onto. So for every choice of B, AX equals B has unique solution. Here, each statements are equal. The columns of A span Rn. That is also same as this one. And here, this linear transformation 1-to-1, then also it is onto. And J and K is quite similar to the original definition of invertible matrices, but here it is requiring only one-sided inverse. There is matrix C such that CA is the identity matrix, or there is matrix D such that AD is the identity. Just requiring only one side, then here automatically the other side will be satisfied. Now here A is invertible, then A transpose is also invertible, and then here we have a property transpose inverse commute, so that inverse transpose, so they are the same. And some more statements will be added in later. Okay. AB are square matrices, and if AB is identity, then both A and B are invertible. And here, B is A inverse and A is B inverse. So that once two matrices multiplication is identity, then here one matrix is inverse of the other. Okay. Use the invertible matrix theorem to decide if A is invertible. One of the statements is satisfied, then it is invertible. Okay. Here, from this one, now let's see in the pivot, and by applying elementary row operations. So once it has 30 pivots, then it is invertible, right? Okay, here 1, 0, -2, and we eliminated this one. 3 times subtraction, 0, 1. 3 times subtraction, that will be 4. And 5 times addition makes 0. And then here 5 times addition, and so that's minus 10. So minus 1, right? Okay. Now here, and if you add, okay, from this one, 1, 0, minus 2, and second row, 0, 1, 4, by adding the second to the last row, we can see that is 0, and there is a 3. So we have now 3 pivots, so it is invertible. So that is exactly this one. Okay, that one. A has n pivot positions. Is now n is 3, so it is satisfied. So it is invertible. Okay. Can a square matrix with 2 identical columns be invertible? No, because once 2 identical columns are there, then they are not linearly independent. One of the statements in the invertible matrix theorem is saying that if A is invertible, then the columns are linearly independent. But if they are identical, 2 columns are identical, then the columns are not linearly independent. So eventually, the given matrix is not invertible, right? Okay. An n by n upper triangular matrix is one whose entry below the main diagonal are 0. So upper triangle has the form. Here now, along the main diagonal, some value is given, but below is 0, and somewhere this area, some value appears. Such a matrix is called upper triangular matrix. When it's a square upper triangular matrix invertible, it should have n pivot positions, which means that every of these diagonal entry must be non-zero. Diagonal entries are non-zero, then it is invertible. That is the only case. At least one of this value is 0, then it is not invertible. Okay? Now we expand the invertibility to linear transformations. A linear transformation T from Rn to Rn is said to be invertible if there exists S, such that S composition T or T composition S is identity for all choice of X. In this case, the S is T inverse. That is quite similar definition for invertible matrices. Also, if A is the standard matrix for the linear transformation T, then A inverse is the standard matrix of T inverse. Quite a natural theorem. And here we can easily prove that, but here we'll not do it. But anyway, this is quite natural theorem. Okay, here T is a linear transformation from R2 to R2 such that it is given in this way, and we want to find the formula for T inverse. Okay. Linear transformation T is defined in this way, then here we can easily see that from T, the corresponding standard matrix A is now here, this one, -5 and 9 and 4 and -7, right? That's the standard matrix. Just to collect the coefficients, then it is a standard matrix. And in fact, originally you learned that, and this first column is action on E1, and the second column must be action on E2, right? So that means here x1 is 1 and x2 is 0, so that is exactly first column here. And E2 is x1 is 0, x2 is 1, so that second column will appear over there, right? So simply, just simply collect the coefficients, then that will be the standard matrix. Now, to find the formula for T inverse, and we may try to get A inverse from here. It is a 2x2 matrix, so that we already know the formula. And AD minus BC, so it is 35 minus 36, so that is 1 over -1, and then, okay, and then change the position and change the sign. So -7 -5, change the position, change the sign. Okay, so here, and from this one, okay, we eliminate the negative sign, 7, 9, and 4 and 5. That's the standard matrix for T inverse, so that we may write down here T inverse of X, so the X1, X2. That is the same as here now. That is the standard matrix. So that 7x1 plus 9x2 and 4x1 plus 5x2. Okay, that's the formula for T inverse. Okay. T Rn to Rn is 1-to-1. What can we say about T? Okay, if T, the linear transformation is 1-to-1, then its standard matrix A for the standard matrix A, and we can say that it's 1-to-1, means columns of A is linearly independent, and also so that now the matrix multiplication will be an 1-to-1 and onto, and here system and AX equal B has always unique solution and so on. So that eventually everything we can say for invertible matrices can be said for this linear transformation. So this T will be onto, and Tx equal some another vector B has always a unique solution, right? So once it is a 1-to-1, then it must be onto. This is the possible when the transformation is Rn to Rn, the same space, okay? Okay, here we have now true or false problem. A is an n by n matrix for every statement. Okay, if the equation Ax equals 0 has only the trivial solution, then A is row equivalent to the n by n identity matrix. Is it true? Yeah, it must be true. In fact, in the invertible matrix theorem, we have one statement like this one. Ax equals 0 has only the trivial solution. So A is invertible. And once, okay, that is another statement. So they must be the same. If the columns of A span Rn, okay, that one is also one statement. Then the columns are linearly independent. Okay, that's also another statement in the invertible matrix theorem, so it must be true. Even though you say the other way, so if the columns are linearly independent, then the columns of A span Rn. Either way, it is true also the same for A. If A is on n by n matrix, then the equation Ax equals b has at least one solution for each b in Rn. Is it true? It's not. That condition, so just it is saying about the structure of the size of a matrix, and now this may not be satisfied. So you already solved the examples that n by n matrix has no solution. So this statement is false. If the equation Ax equals 0 has a non-trivial solution, that means that there is at least one free variable. A has fewer than n pivot positions. Yeah, it's true. Because at least one free variable. So the basic variable should be less than n. And so here, A should have fewer than n pivot positions. If A transpose is invertible, then A is, okay, not invertible, then A is not invertible. Yeah, it must be true, right? Once A is invertible, then A transpose is invertible. That means that if A transpose is invertible, then A is invertible. So one of them is not invertible, then the other must be not invertible. Okay, so it is true. Finally, if the equation Ax equals b has at least one solution for each b in Rn, then the solution is unique for each b. Okay, is it true? I guess you have to think a little bit deeply for this problem. Okay. Now, at least one solution exists for every choice of B, means that here columns of A span Rn, right? And at least one solution for each B means that each column, in fact, each row has a pivot position, right? So without that, here, for some choice of B, it may not have a solution. So each row has a pivot, which means there are n pivot positions. That means also A is invertible, so that the solution must be unique, right? Once matrix A is invertible, then linear system has unique solution. And if we consider this matrix multiplication as a transformation, then this transformation is 1-to-1 and onto. So invertible matrices have really wonderful properties. The last statement is true. Okay, that's the end of section. Thank you.